Okay. Now, let's talk about the recursion step. And for this one, we are asked to find these, and these, given these, right? And I think a lot of it, so actually a lot of what we have written came from the above, right? Because, well, for example, this we have calculated above, this we have calculated above, this, these, yeah, these four we have calculated above. And the rule to remember here is actually pretty simple, and it comes back to the fact that all velocities are differentiated in the inertial frame and then translated into other frames. So to translate it back into the zeroth frame, the inertial frame, they are only related by rotation matrices. So I think this one is the easiest one to get. So A0 from 3 to 0 is just equal to A from 2 to 0 times A from 3 to 2. It's just a chain rule, and what in the middle goes away. And so this is the easiest one to get. Once you've got that, R30 is equal to what? Well, it's equal to, well, there are some of them that are given. So, it is just R02 plus a 3 to 0 times this one's a little weirder. Oh, of course. A 2, 3. Two. So this, we're looking for the position of 3 in frame 0. This is O3 and O2. We have to add. Well, algebraically, if you just think about it, we have to make. We have to add this vector, and this vector can be simply be done by multiplying A0, 2, 0 with R2, 2, 3. That makes sense, and for us this one is already given, so that's great. Okay, now comes V0, 3 to 0, and it's actually this exact same fashion because it's V2, 0, and it's actually plus this one. And lastly, this one. Oh, I forgot something. So let's write it here instead. So omega 30 is equal to omega 0, 2 plus a from 2 to 0, omega 2 to 3. So that is our recursion. So now, this is completely according to formulas. We don't even have to remember these because first, the algebraic rule is that what in the middle goes away, and secondly, it follows the vector calculation rule. So this one is 0, 2. Imagine there's a 0 here. 0, 2 plus 2, 3 is going to be 0, 3, or, that one. And that is how we work with the indexes on the right. And how we work with the indexes on the left is just that, well, the rule number 1 is all vectors has to be in the same coordinate system in order for it to be added together. And the second rule is for rotation matrices, what in the middle goes away, so this one actually evaluates to omega 2, 3 in 0th frame. And we can here confirm here is the in frame 0, that's frame 0, that's frame 0. You can safely add them, and that's done. What I want to understand here, however, and well, if this is just a task in the exam, we could stop here, but most likely in the exam we won't have this kind of task. So we have to actually, they will probably give us numbers and something, and we have to understand what is, for example, omega 3, 0. What does that even mean? Well, omega 3, 0 is the rotation speed of the third one, which is right here. And it's rotating like so, and we want to express that in the frame 0. And that would look something like this vector. What about omega 2, 0? Right? Well, it's actually very, very interesting because, well, I forgot to mention, but omega 3, 0 contains the rotation of this one, but also it contains the rotation of this one added to it. So these two rotation speeds, so this is Q3, I think. This is Q3 dot, and this is Q1 dot. So Q1 dot plus Q3 dot actually equals omega 0, 3 in this case. Of course, that is only true if the Z1 and Z3 axis aligns. And in this case, if you look on this graphic, they do align. But in general, this one is its own vector. It could be, like so, and this one is its own vector, which, could be something else. And the sum of those two vectors is the angular velocity omega 0, 3. Now the Q3 dot, right here, when I express this vector in the coordinate system 2, so this thing, since it rotates, the third one rotates like this, its omega vector is something like that, but if I write it in 2, it would have something like 0, negative omega and 0 if I am to write it in coordinate system 2. And this vector, this vector 0, negative omega, and 0 is what flows into this one, the omega 2, 3 expressed in 2. It's just the relative rotation speed between the third axis and the second axis expressed in the second axis. And now I have to actually take this entire vector and rotate it from 2 to 0, right? So I have to multiply it, and well, you could imagine, writing out that gigantic matrix and multiplying, and at the end you will get out something in the 0th axis. But at least in this case, you don't have to do that. You don't have to look at that. Why? Because in principle, it's actually just translating this same vector to coordinate system 0. Well, I mean, you don't have the coordinate system 0 here, but I can already say, even without having access or having written the axis 0 explicitly written here, according to the DH convention, Z0 is here, and I can already see it aligns perfectly with the omega 2, 2, 3. These two vectors aligns, and so without even having to draw in, for example, y0 or z0, they could be anywhere. I can already see that this entire expression evaluates to something like omega 0 and 0. And the rotation speed of 2 in frame 0 is also just entirely a z-axis vector. So everything just kind of works out. So I can also add it to it, something like, oh, my screen went blank. Oh, it's back. Omega, actually 0, 0, and I guess omega 1. I don't know. And omega 1 is just, how fast this thing is rotating. And it's also in the z component only because, well, this is how it's aligned. And yeah, that works out exactly to be how the third axis is rotating in the 0th frame. It's just the sum of its own rotation speed and this thing's rotation speed. And so that is the intuition behind these formulas.